Okay, so what we've said before was that the Laplace transform of f of t, of any function, is defined as the semi-infinite integral, positive infinity and 0, of the function f of t e to the minus st dt, which we can also denote as f of s. And we solved we derived the Laplace function of f of t when f of t equals a constant, which was just a on s in the previous video. So now let's try doing another one of the Laplace of transfer function of e to the at. Okay, so if we think about this just conceptually, e to the at is going to look something like, if this is t, and if that's f of t, it's going to look something like that, yeah? Passing through a, yeah? And e to the minus st is going to look something like this. Now, do you remember what we said? And that's going to be passing through s, wherever that is as well. Now, do you remember what we said before was that the condition for Laplace of this evaluating this integral is that the product of the function and e to the minus st is such that when t tends to infinity, the product of these two functions tend to 0. Now, if s is too large, i.e., if s is too large, meaning something like this, yeah, I've done that a bit wonky, but you get the idea. If that's a larger value of s for the negative exponential function, then what's going to happen is that it's not going to decrease at a rate at which it's going to tend to 0. So as t tends to infinity, the product of this function and this function will actually tend to infinity, and that's not something that we want. We have to ensure that the product of those two functions are such that f of t, let's say if this is f of t, and this is e to the minus st, is such that when you multiply them together, as t tends to infinity, the product is going to tend to 0. Okay, and that's going to be important when we evaluate this function here. So let's go back. Laplace, okay, of e to the at is going to be defined again as the semi-infinite integral between infinity and 0 of f of t, which is this time e to the at, e to the minus st dt. All right, now we can simplify that to simply e to the t a minus s dt. And now let's actually perform the integral here. So we can say that's simply going to be 1 over a minus s e to the t a minus s, evaluated between infinity, positive infinity, and 0. Now, let's see what happens. How are we actually going to evaluate this at infinity and 0 here? So when t tends to infinity, what's e to the power of t a minus s going to equal? Let's think about this carefully. If a is greater than s, let's say if the magnitude of a is greater than the magnitude of s, then we can say that e to the t a minus s is going to tend towards infinity as t tends to infinity. Yeah? Because what's going to happen is that when t gets really, really large, and this is positive, if a is greater than s, then this argument, or this you could say is kind of a coefficient, is actually of t is going to produce a positive exponential function like this, isn't it? And that's not what we want for Laplace. That's never going to work. We have to try and ensure that as t tends to infinity, the product tends to 0. How's that going to happen? Well, if the magnitude of a is less than the magnitude of s, then we can say that this is going to be a negative exponential function. As t tends to infinity, e to the t a minus s is going to tend to 0. So we just write that out. E to the t a minus s is going to tend to 0 as t tends to infinity, providing, and this is really important here, V-I-D-N-G, yeah, English, great, providing s, the magnitude of s, is less than the magnitude of a, i.e., we can say that s has to be sufficiently, providing the magnitude of s, that's wrong, is greater than the magnitude of a, yeah? So here we can see the result of what we've said before, was that s has to be sufficiently large such that the product of both functions are going to tend towards 0 as t tends to infinity. That's going to happen providing that s is greater than a. So that's what we mean by saying, when we say that s has to be sufficiently large, of f of t e to the minus st to t. So assuming that is true, assuming that s is sufficiently large, then as t tends to infinity, this whole product here is going to tend towards 0. So we can say this is going to be 1 over a minus s, 0 minus e to the naught, which is 1. So that's going to be 1 over a minus s, 0 minus 1, which equals 1 over s minus a. Therefore, we have our next result of the Laplace transform of e to the at is simply going to be 1 over s minus a.